China. He pursued a PhD at Princeton University and obtained in the year 2000. And then he spent some years as a member of the Institute of Advanced Studies and finally moved as a professor at the University of Arizona. He was awarded several prizes and fellowships, including the John Simon Guggenheim Fellowship, the David and Lucille Packard Fellowship, the Newton Lacy Pierce Prize, and the Alfred P. Sloan Research Fellowship. Xiaohui is an observational cosmology, and sometimes when talking with my friends, I describe him as the Lord of the Quasars. He and his group have pioneered techniques to search for the most distant quasars in the early universe at redshift higher than 6. And uses these quasars, he has shown that supermassive black holes with masses up to 10 billion solar masses existed within 1 billion years after the Big Bang. Currently, he and his group hold the records for the most distant confirmed quasar and the earliest supermassive black hole. A few years ago, he discovered also a gravitational lensed quasar at the end of the epoch of reionization, the first of its kind. And today, he will be speaking about quasars and the intergalactic medium at cosmic dawn.
Thank you, Fabio. Thanks for that introduction. So this is the first time I give a talk in 2 years without mask. So I'm sure it'll rusty, so just bear with me. We'll see how it goes. So as Fabio said, we're going to talk about parachute quasars and in the relation to black hole growth, the host galaxies around it, how they're interacting with galaxies, and of course also how they can be used to probe of the cosmic reionization and the universe transform from mostly neutral and higher redshift to mostly ionized and lower redshift. This work is done with collaboration of many collaborators listed here, but I want to highlight in particular these 3 people, Jinyi Yang, Figure One in Arizona, and Eduardo Venados at MPIA. All right, so it's not advancing. Okay, so first quasars was discovered actually almost 6 decades ago now. Of course, since then, quasars has always been one of our primary tools to study the evolution of the universe from the current epoch to whatever the highest redshift frontier is. I remember the last time I gave a colloquium here was probably a little bit more than a decade ago. And that was the spectra that I showed at that time. That was essentially all the quasars we know at the redshift close to epoch ionization, sort of 2010 also. There are a handful of these objects at that time. But even then, as Fabio actually already described, the things that you learn about these objects is that first, the strong absorption on the blue side of this landmark emission line, which now redshift to 9,000 angstroms, tells you the universe is quickly changing from very high ionized to becoming more neutral when you go to higher redshift. And also the existence of these objects, very bright quasars, those redshift tells you sort of billion solar mass black holes already existed at the end of reionization. Well, since then, more than a decade passed, and we have just a few more quasars there. This is the first time I made it. I actually don't know how to make this plot to make the point yet. So if you have a good suggestion how to make like 500 spectra on the same plot, let me know. But what you can see here is now, first of all, there are a lot of them more. A lot of them now. There are actually 1,000 quasars from various surveys which have 5, 200 now which have 106 compared to the one that we had before, and about 10 quasars at redshift higher than 7. So the frontier had moved on to redshift 7.5. And at close to the end of reionization redshift of 6 also, now you have very large samples that give you statistical information rather than just individual line of sight. But of course, using quasars to probe early universe is not a new idea. I think the point of what quasars are doing there is actually very nice summarized by Martin Rees in one of the review papers that he, more than 4 decades ago, said the study of distant quasars, an attempt to detect them at even higher redshift, of course that's what we do, are thus critically important for the study of galactic evolution. And all the problems are so interrelated that we will not understand the dynamics and kinematics of the cosmos until we have clear perception of galactic evolution of what happened in the active nuclei. That's really the point of what quasar is helping us to understand the early galactic evolution and evolution in the galactic medium. So I argue that you actually do that over very large order range of spatial scale, over 10 order magnitude, and zooming into sort of 3 scales and 3 questions that I'm going to talk about today. One is at the scale not much larger than a horizon, at the scale of accretion disk, the scale of boson-like regions. We're using the quasars we observed today to study sort of how they are seeded and how they grow to be the earliest supermassive black holes in the universe. That's the first thing I want to talk about. Then a few of them in the larger scale is the scale of galaxy formation. So we want to see what quasars are doing there to their galaxies, and whether galaxies and their host quasars and black holes in the host galaxy are co-evolving a cosmic dawn. And I'll show quite a bit of really ALMA data, and thanks to those people who survived ALMA deadline today, to probe this problem. And finally, at even larger scale, another few elements bigger. This is from the simulation that's done locally here. We're using these quasars to probe the history of cosmic reionization. So that's the 3 questions we want to touch on today. The things that enable us to do that in the last decade that is much, much better than we were able to do 20 years ago was because of these new optical and infrared photometric surveys that allow us to essentially carry out all sky surveys of these distant quasars, because quasar density are lower at higher redshift. Therefore, you really need deep, wide angle and surveys that cover both optical and near infrared and mid infrared wavelengths to be able to select them, detect them, and be able to tell these are photometric selected quasar candidates from other contaminants such as brown dwarfs, such as early type galaxies, and then go to do sort of hard work of doing spectroscopy to identify them, to measure the redshift and measure the properties. So all the combination of their surveys that in the last few years have really covered the most part of the high galactic activity in the sky already, that allow us to essentially begin to clean up all the quasars we can find up to a certain, down to a certain luminosity or flux limit. And in fact, they're showing really here. So that's the progress of the sort of redshift 5.6 quasars as a function of published years. And you can see about 6-7 years ago, when we begin to have these all sky deep optical imaging survey, optical and infrared imaging survey, the number just go up. And this is sort of the put the quasars on the absolute magnitude, sort of UV magnitude of -26 or something, and redshift. So this part of the diagram is really populated at redshift 6 to 7 over a very wide luminosity range. So these are older covering of the range of sort of almost 10 magnitudes, so a factor of 10,000 in flux, right? And the highest redshift frontier now is the 3 optics at redshift 7.5. So before we talk about the astrophysics, let me just highlight a few of these, my favorite quasars at that time. There's this one. This clearly stands out. It's a redshift 6.5 quasar that has appeared to be 15 magnitude. I mean, if you're an optical astronomer, you know that's not something you should associate with quasars at the end of the universe. What is that? And then I'll talk about 2 even newer discoveries at the redshift frontier. So just as actually Fabio mentioned, this one is actually the most distant lensed quasar we know at redshift 6.5. The reason that it's so bright is because we think it's magnified a factor of 50. Then this is a confirmation of the lens of the lens nature of this object. Has a galaxy next to sort of 2 images. It's actually rather weird and tricky lensing model that allow you to have a very high magnification, but right sort of close to the edge of acoustic. And because it's so bright, you actually allow you to do all kinds of neat things. It's the brightest object in the early universe in almost every single wavelength that allow you to, we actually have a very good X-ray spectrum of the object from XMN. We actually have many, many conditions with ALMA that probing the atomic and molecular lines of the object. And we'll talk about this ALMA image and how they can zoom in to very close to the black hole a little bit later. So that's the first example of this. This object was discovered or published in 2019, so right before it started. The second object was an object that we published actually during the pandemic. Is a redshift 7.52 quasar. So one of these 3 redshift 7.5 quasars that we know today. It was the first object we know at those redshifts that contained a 1 billion solar mass black hole. So redshift 7.5 with a 1.5 something billion solar mass black hole. as indicated by measuring sort of the broad emission line width of this object. This object also has a, I'm not going to try to pronounce it, it has a Hawaiian name that we worked with local Hawaiian Big Island teachers actually to come up with a name that has a very nice meaning. And that's actually just the first quasar that got a native name because the object was discovered in Gemini, so we thought it was a really good outreach to do. So finally, this is the highest redshift quasar we know today. At redshift, we published today at redshift 7.64. It was published about a year ago. This is the current redshift holder, but beyond that, the interesting thing about this object is that you can see here, so that's a Lemma alpha line, which clearly is absorbed by a lot, but the region is absorption of the Lemma alpha line compared to sort of this blue is like a template for lower redshift, is that there are a lot of absorptions that are highly relativistic, so like 0.1 to 0.2 C from nanolines in the quasar. So these are outflows. These are relative outflows coming from the quasar. So even at the highest redshift, you see this clearly doing something kinematically to the host galaxy already. And this kind of so-called broad absorption quasars are not uncommon, but they seem to be even more common when you go to the highest redshift. Okay, so these are the three examples of the highest redshift. Now the question is, now how can we push even further? So this plot summarizes the evolution of quasar number density at sort of relatively bright end. These are your typical, what we call the Sloan quasar, typical bright quasars as a function of redshift. So the quasar density peaks, the redshifts are like 3 or 2 or 3 also, then just decline. And the highest redshift we can measure the luminosity function or the density is about redshift 7, which is more than 2 orders of magnitude lower already. So these objects are rare. They are 1 per cubic gigaparsec also. So even the largest sort of good cosmological simulation can only produce 1 or a handful of these objects or the largest volume possible. And the other thing we noticed that is when you go beyond redshift 5, this sort of exponential decline getting even steeper. So this rate is even steeper now, it's even more than the exponential now. So quasar evolution seems to be have accelerated even higher redshift. Well, that of course is both exciting and disappointing in the sense that exciting because we are looking really, really close to when you can ask the question of when is the first quasar, depending, of course, the luminosity dependent. If you just draw a line here and let's keep on going. For this kind of object, basically these are objects of billion solar mass-ish black hole in them. You can get 1 quasar in the entire 4 pi sky. So 1 quasar is within our cosmic horizon at redshift 9 to 10. So exciting in the sense that we are finally going to answer when the first quasar at certain luminosity appeared. Disappointing means that there's not much thing to do anymore, so I have to find something else when you get to redshift 9 to 10, probably in the next decade or so. And you can actually predict when you're going to do that or how you can do that. Basically is by extending the current sort of wide field survey to the infrared wavelengths to deeper, to greater depths. And that is possible by combination of optical sort of survey of Rubin, which basically gives you a dropout band for the absorption, and then Euclid and Raman that gives you the infrared coverage. So in the next decade also, we'll have those data. Identifying them is not going to be easy because you're fighting with even worse kind of contaminants coming from all the foreground stars, galactic stars, or strong dwarfs and the low redshift galaxies. And these are going to be 23, 24 magnitude, 25 magnitude, and in the infrared. That means the current generation 8 to 10 meter telescope is not going to be good enough. You either have to use HST or ELTs to actually get their spectral and actually measure the redshift. But we think that in the next decade, the thing here is that for the brighter quasars, we're actually getting very close to getting to the highest redshift possible. All right, so that's about the quasar discovery. Now I want to talk about what we're going to use these quasars for. So the 3 questions: the black hole, the galaxy, and reionization. So first, talk about the black holes. So the way that we know what's going on in the black hole is we have a way of measuring black hole mass in these quasars. That's the only way that until recently, until in the near future, the only way we know how to do it is to use the broad emission line in the quasars. These are emission line from broad regions that are sort of same scale of the accretion index, so well within the field from the galaxy. as it's all the black hole. So you're assuming that the line width, the kinematic of the line is dominated by the gravitational force of the quasar or the black hole itself. So you can use this as a way of measuring basically V, velocity, carrier velocity. And then the R, the size of the boron region, is sort of it's a local empirical relation that the size of boron region is proportional roughly to luminosity to 1/2. You can think of it just like that photoionization give you. And then you can calibrate this relation locally and get a black hole mass. That's all the black hole mass that we know so far at cosmological redshift in quasars have been, even in non-quasars, have been obtained. And this is a summary for our sort of redshift 7-ish sample that was published last year by Jin Yang, using essentially this particular line, magnesium 2, which is sort of good line to use to measure these quasar masses, the black hole masses. You can see sort of clustered around the 10 to the 9 solar masses. So that's a statement of 10 to 9 billion solar mass. I mean, 1 billion solar mass black hole exists at the highest redshift. But beyond that, we even have more extreme examples. This is an object we discovered more recently, seem to have a black hole mass at least 10 to the 10. So now we have a 10 billion solar mass at redshift 7. I said it's upper limit, lower limit, because this object seemed to be a little bit dust reddened or obscure. So we actually don't know what the true luminosity is. So those objects are the objects that give you the strongest constraint on how fast and how early supermassive black hole mass grow. The other thing is when you get the black hole mass, you get luminosity, you can get to the accretion rate from the luminosity and compare that with sort of adding to luminosity and getting sort of how fast the quasar is accreting. And here showed here is the black hole mass versus volumetric luminosity. This line here is when the quasar is accreting at maximum Eddington rate. And you can see that most of these redshift 7, 6 quasars are clustered around this line, not very much deviate from it. The measurement of black hole mass itself had nothing to do with Eddington limit. And the fact that they're actually not super Eddington, that tells you there's something, even though it's an empirical sort of scaling relation, the relation actually works statistically, because quasars don't really, the way you measure quasar mass, they don't really shine at super Eddington. And they are sort of clustering around Eddington ratio of 1 also, compared to this blue one is sort of low redshift matched, luminosity matched. So these things are accreting about as fast as they can, as those redshift, and as mass as high as they can. As high as you can get in the local universe. And that's the plot sort of people like to use in this kind of discussion is, well, if you assume that this is the best you measure at those redshift you observed, and you assume they're growing at Eddington limit, which is what we observed, and assuming that they're really growing continuously 100% duty cycle, and you just exponentially drop the mass to wherever you think the seed black hole was formed, and that tells you these quasars we have, assuming this model, you'll get 10 to the 3 to 10 to the 4 solar masses, even if the initial collapse is redshift 30. And that is why people talk about whether they can be remnant population 3-star, probably not, or collapse of dense clusters to really need more exotic models like direct collapse black holes that some people here are working on to produce the supermassive black hole that we observe today. I'm not going to talk about exactly which this model works. The reason is I think we're very observationally, we're still very far away from actually answer the seed question other than the simple extrapolation. The reason is, well, there are probably 2 ways of solving this problem, and the 2 ways, one is have very massive seeds, direct collapse of 10 to the 4, 10 to the 5 solar masses at certain redshift, and then you can have Eddington equation to get there. The other is maybe you have phase of really inefficient or obscured accretion that is much higher than Eddington rate that can get you much faster with even a smaller seed. We have no constraint about exactly what happened during this area. We only observed these quasars at the end of this accretion process when the quasars seem to be not obscured, they seem to be at accretion Eddington rate. Even more so, these quasars don't look young at all. I mean, Christina can tell about young quasars, but those quasars look old by and large. And that is when you look at the red curve, which is actually an average spectrum of quasars redshift 7, compared to the black one, which is an average spectrum of redshift 2 or 1, they don't look very much different. You have all the emission lines, broad lines pretty well here, except this is the carbon 4. The carbon 4 look a little weaker and sort of tilted or more asymmetric, which actually is an indication of more outflow in these optics. Otherwise, they look very similar. Another way to look at it, if you can look at all these metal lines, there are some iron features here, there's magnesium 2 here. Those line ratios are constant more or less across cosmic time as well. So we're not looking at spectroscopy speaking, or structurally speaking, we're not looking at the first quasars yet. And the key of answering what are the seed black hole is really relying on uncovering this part of the diagram, sort of the 10 to the 6, 10 to the 5, 10 to the 6, 10 to 7 solar mass black holes in those systems. And that's not something we can do with the most luminous quasars. And I argue that the needs to go to reach fainter, earlier, and more acute phase of black hole growth is the key, which is beyond what we can talk about with optical infrared surveys, and probably have to rely on X-ray surveys, such as maybe some link light or something to do that. And that's really important. Otherwise, we're not going to get to the seed or get to the order magnitude light, get to close the seed. We're only getting the end product of it. And one of the indications of these obscure quasars exist is this new work that's led by a grad student in Arizona, Ryan Antley, where he discovered in one of the deep field, there's a lemon dropout object that actually have a strong BLA counterpart. So clear there's an AGM in it. And then we were able to confirm the redshift and show that this is a properly obscured AGM buried in the Lemon Break galaxy. So these obscure things do exist at much fainter level. We just need to have a much larger area, more sensitive survey to actually find them to understand their properties. Okay, so that is the first topic, the black hole seeds. I think the bottom line there is that we do see very massive end products, but we are not close to find out the seed, what's going on in the seed yet. The second topic is really the thing that make a lot of progress in recent years, is to understand black hole and quasars and their host galaxy and their environment at the highest redshift. Okay, let me just start by saying that this is still impossible to do with optical and infrared observations. These are probably two best examples of people's attempt to detect quasar host galaxy using HST. And the end result of this work is basically you have sort of a good upper limit. There's no, these are just noise. There's no clear evidence. These are just the noise from subtracting out the PSF and the residual of it. So even detecting stellar light, even with HST, are proven to be difficult to impossible and challenging. So we don't really know what stellar light look like for these quasars. What we do know, and what people are doing in the last really 15 years, is to go to much longer wavelengths. So this is the spectral distribution of a quasar at a shorter wavelength dominant accretion disk. You're dominated by the dust coming from the AGM itself. And then when you go to the longest wavelength, you begin to get to the sort of far infrared cooler dust, presumably heated by star formation. And what that gives you is dust continuum that is tracking the dust mass and tracking the far infrared luminosity connected star formation rate. There is the strong cooling line, carbon C plus 158 micron, which because it's so bright, it can allow you to actually get the signal to map kinematics of the host galaxy. And then finally, the CO ladder is going to tell you about cold gas as well as sort of heating of the nuclear gas in the quasar host galaxy. So most of the work I've done so far is on the dust, the C plus line, and various other lines in the far infrared sub-millimeter wavelengths. Even though the idea is simple, observation used to be really challenging. We started doing that. People started doing that from early 2000. And at that time, you have sort of the ERA 30 meter. You have at that time, the viewer now is NOEMA. And then we have VLA. This is a poster child of the high-risk quasar of the last decade, which is the first object that actually was resolved at those redshift with a very high star formation rate, star intensity, and various line detections. But that was like hundreds of hours combine these telescopes to get observations like that. That's where ALMA comes in, of course. ALMA really is transformational in this field because of the sensitivity, because of the resolution. Now you can actually observe the same kind of detection of this object with snapshot survey of 15 minutes. And within 15 minutes, the quasar we're talking about is almost 100% detection rate in continuum and C++. So that's just a survey of these objects that have snapshot that not only detects them for some of the objects, you can even marginally resolve them even in low resolution. And then you can really go to high resolution. And that's really exciting because that is when you actually resolve the dust and the gas and can compare with simulations and do some real astrophysics. And that's just an example of two of the objects that we observed recently that have very high resolution of about 0.04 to 0.08 arc second. So these are HSDL resolutions on ALMA. That corresponds to physical size of just a few hundred parsecs at those redshift. And these two examples, the two objects that we studied recently, they have a similar black hole mass, but they have very different look in their ALMA high resolution image. One is much more extended. You can even argue whether there's a cavity or not in the middle of this is the C+ line. This is the atomic emission. And the velocity field, this is the velocity field looked messy. And then the other object looked much more compact, but had a really nice velocity gradient in the middle that make you wonder whether this is rotational support or not. So these are the kind of observations that we'll begin to do now. I'm just going to highlight some of the sort of the overall property of these objects and highlight one particular object later. So overall, what we see is from this kind of snapshot surveys, we can begin to plot a lot of quasars. Now I think they are not quite 100, close to 100 objects that are detected in the far infrared continuum at redshift sort of 6 to 7 range. And they are bright. Their far infrared luminosity is 10 to 12 to 10 to 13, maybe even higher solar luminosity. So these are your typical ULERG or HIDE-LERG or something. And if you translate that far infrared luminosity to star formation rate, that's 100 solar mass per year, that's 1,000 solar mass per year. So they are clearly forming stars like crazy. They have a lot of molecular gas allow you to do that. So they are clearly the site of some of the earliest massive galaxies. In fact, that's probably the most massive galaxies in the early universe. Well, that's of course not surprising because we're looking at the rarest object high redshift. So the other conclusion is that first, there are a lot of dust emission in them. That tells you these are have a lot of star formation in them, a lot of dust in them already. These are massive galaxies that are even metally rich, even at the highest redshift. The other thing is, I showed that plot earlier, these contrast these two objects that we see is that they are really not the same. When you look at them, there's a very large dispersion in their properties. If you can look at their kinematics even. So this is again C+, so the atomic line, and that velocity field. In the beginning, I think when ALMA first turned on, our first few objects showed this nice rotation curve or velocity gradient. At that time, we're like, wow, these are all disk galaxies at redshift 6. That they do exist. These are rotation that can be fit quite well with sort of a disk with some dispersion dynamic model. But then when we look further with more objects, other things can pop up. Some objects that don't have any older motion that seem to be some kind of dispersion, turbulent, whatever dominated. Some objects are very disturbed that have tails or have close companions that are clearly in merger or something. So basically it's 1/3, 1/3, 1/3. 1/3 of them look like have strong older velocity gradient, 1/3 look dispersion dominant, 1/3 look perturbed. So clearly they are the site of these massive galaxy formation in the universe is diverse. But in general, these are objects with compact morphology. So the half-life radius is just a couple kiloparsecs compared to the low redshift galaxies are bigger. They are turbulent even those objects have high velocity dispersion in their disk. They have large star formation as I mentioned. They are massive, and the average kind of dynamical mass you can get from at least on this object you can model them is sort of 10 to 10 to 11 solar masses. So these are very massive galaxies at times. And they have high mass fraction that you can derive from either the dust to sort of using the dust or using CO to get the gas mass compared to their dynamic mass. There are a lot of gas in it. So that's why they're forming stars. So just to show you two examples of these measurements, this is from a very recent work that used a higher resolution ALMA data to do this, to allow for a dynamical modeling of these objects. and you can separate sort of disturbed morphology with non-disturbed morphology for different samples. But that's a sample. This is the velocity dispersion in the dynamic modeling after you subtract out the older motion part. They are 100 km per second-ish in their sigma. So this is not going to be very stable. That's probably why they're falling stars like crazy. And this is the gas mass coming from the dust, so assuming some kind of dust to gas correlation, and versus dynamical mass, this is 1-to-1. So these objects have a lot of gas in it as well. So that seems to be the picture that we see is that they're high star formation rate. They don't look the same, but they all have sort of a lot of star formation rate, a lot of gas in it, and they seem to be turbulent. And of course, with the dynamical mass, if you can measure it, or even if you can measure it, just looking at sort of the line width of your emission lines, again, use that the proxy of some kind of sigma or some kind of velocity dispersion or something, is tempted to put them, of course, in the black hole mass versus dynamical mass or sort of n sigma relation kind of thing. People argue about exactly what that means, but I think at least observationally, it's clear that no matter how you do the dynamical mass part, whether you're just using line width, whether actually do careful dynamical mass modeling, they give you the general same on average that most of these quasars, especially the high luminosity ones, are sitting above this M sigma relation locally by a factor of, on average, about order of magnitude. They are objects that are on the relation. They're objects, especially low luminosity, they're objects along the relation. But certainly in high luminosity, there are a lot of them are really above it. You can argue how much selection in fact play into it, but at least for the object we can model, they seem to be all above it. And that is one thing that is really interesting, would be to compare that with a simulation that actually can simulate the kind of kinematics of these very massive galaxies early on with black hole in it, because this more recent work actually compared all different kind of simulations. Some of them are produced here, and with the sort of the deviation from the local M sigma relation, where function of redshift for different kind of quasars, and you can see they don't really agree. The models don't really agree yet. But our observation for bright quasar is like here. So clearly, we want to improve the model. We also want to go to larger sample with less biased fainter quasars to probe exactly how black holes are, whether these black holes really overmassive compared to the host galaxies, whether it's sort of the active growth phase of these luminous quasars really preceding the full assembly of the galaxy themselves. So one question in this is the black hole mass. And that gets to something that I think is really exciting, and that's where we're doing last few days, read a whole bunch of ELMA proposals to think about it, is whether you can actually do more with ELMA, whether you can actually measure the black hole mass itself, rather than using some kind of scaling relation that we observe locally. The first object I think we can possibly do that is this redshift 6.5 quasar I mentioned earlier. This, like I said, is the brightest quasar there. It's bright in every single wavelength we looked at. And is also highly magnified. That not means that it's more luminous, also means like stretched, so you can have higher resolution. So this is the low resolution ELMA data that come from a few years ago that were published that shows this nice arc. And that's a counter image over here. The optical image is like right in the middle, but the host galaxy already stretched to an arc. And you can also see there is a very clear velocity gradient along the arc. So clearly this object is some kind of velocity gradient that look pretty ordered. Because it's bright, you can actually do high resolution study. And because it's high magnification, you're zooming in to the very center. Let me just show you what the high resolution image look like. This is 0.05 arc second now. So we haven't reconstructed the velocity field yet. So I cannot tell what the answer is, but based on the lensing model, the most highly magnified part of it have a sort of effective resolution of about 20 parsec at redshift 6.5. So that really makes you think maybe we're able to actually see this is going to be within the sphere influence of the black hole. Maybe we're going to see a nice capillary rotation and matter black holes. So that is something that I think will come up in the next few ELMA cycles, especially with, I think this cycle they're offering even higher resolution or not. So maybe we'll get some of these 0.02, 0.03 arcsecond resolution images, not only the lens one, but the normal one as well, to actually see what is going on within the central 100 parsec of these quasars, and whether we're going to see the motion in the gaseous states. The thing that we did before that allow you to map, to survey all the quasars, is actually one of them is to allow you to find objects that are bright or compact at good velocity gradients that allow you to do this kind of thing. So that's what I'm really excited about, is in a few years we may be able to actually see the black holes influence, whether it is through their gravity or whether it is through feedback in these very high energy quasars that closest to the black hole. All right, so now let's move on to, I think, the third topic. So the third one I want to talk about is the history of reionization. Many people here work on reinizations in many different angles, whether it's through theory or whether it's through multiple way of observing them, through CMB, through Lemma alpha galaxies, and future through 21 centimeter. They will argue that Quasar provides sort of a unique multi-probe of this problem that others don't. CMB and sort of galaxies with high redshift give you a nice overall global constraint of history. Obviously, 21 centimeter is going to resolve everything, but we're probably still a few years away from that. But what Quasar does is actually give you individual line of sight, and you can probe various things along this line of sight to know exactly where things are happening. And these various things, including just looking at the absorption at somewhat lower redshift, lower than redshift 6, also just look at absorption coming from Lemma forest and the transition in them to map the end of reionization just through optical depth measurements from sort of the neutral hydrogen absorptions. Metal lines tells you how IGM and metal enrichment may be connected. And the area very close to Quasar I will mention later on give you other probes of really the peak era of the reionization, exactly how quasars, how intergalactic medium is chipping away emission even on the blue side, on the red side of the Lemma emission line. So there are multiple probes when you go from the quasar to us, when the quasar light passes through the intergalactic medium, that tells you something about IGM evolution. Of course, those things started from sort of your classic Gunn-Peterson test, which that was the first detection of Gunn-Peterson 12 from sort of the first redshift 6 quasar 20 years ago now, where you see finally at redshift 6 also IGM is becoming opaque. That was the first 12. Again, just like when at that time we have a handful of quasars can do this, now we have many. So instead of mapping one of these 12s, we can map many of them. Now we can actually see a map of these Lemma transitions by just stacking all the, sort of putting all the spectra together. So the thing I want to see here is that this is redshift. These are basically just one-dimensional absorption spectrum of quasars, and these are just absorption redshift go from low to high, and these are individual sightlines that you're probing. And the grayscale is the transmitted flux, is how much flux is coming through. So when you go to red color or the dark color, there's no flux anymore. That's complete computing control. So what you see is actually from low to high redshift in this direction, quasar is turning, the sightline is turning opaque very quickly. But the two things that are things that people realize more recently, one is that even when you go at relatively low redshift, there are high contrast in different troughs. And that highlighted in that particular example that sort of George Baker in his work highlighted. One of the sideline at redshift 5.5 or so right here, I don't know which one that is, it's completely black. At the same redshift, other sideline can be very, very transparent. So at the end of reionization, things clearly is fluctuating a lot. And you can see the thing here is not uniform at all. And when you go to high redshift, then things become dark, but there's still occasional transmission spike. The highest transmission spike I'm aware of that we think is real rather than some noise peaking data is redshift 6.7 also. So that is basically when you're running out of probe for these Lemma alpha absorptions and everything becomes completely dark. But in between those, that's where Lemma alpha transmission probe are still useful, and especially the fluctuating part is very interesting. And that's a summary of sort of all the Lemma alpha absorption measurements that we published a couple of years ago, where you can see, and all the other works that, including published by other people in this room, that at redshift higher than 5.5 or so, things just begin to take off. So there are a lot of complete absorption troughs over here now. That's the individual sightline. This is a very high redshift since a lot of the sightline are pretty opaque. We're actually doing stacking to get a better limit. So the transition accelerating at redshift 5.5, but at low redshift 5.3, 5.5 or so, there's a huge amount of scatter compared to mean relation. And of course, when you go to redshift beyond 6, as I mentioned, there's complete troughs, but and with the very last bit of transmission in redshift 6.5, 6.7 also at some occasionally happen in some sidelines. And this increased scatter is what makes people wondering about what is the end of reionization, whether reionization will end is 6 or 5.5 or even earlier. And that's because if you're assuming sort of like that's Christian Eller's work, if you're assuming that this is the probability distribution function of the optical depth, so how opaque the line of sight is, that's observed result, and it's a different models that you can see that sort of a uniform ionizing background model doesn't work. So you have to have a lot of scatter either in the temperature or probably more likely in the background itself. That gives you the increased scatter here. That tells you reionization probably have not quite completely done by even redshift sort of 5.5 or so. So there have been more and more suggestions of loss of island of neutral hydrogen may extend to fairly low redshift. So I think one thing new in the last few years is we used to say redshift and we used to say reionization end around redshift 6. That's still true statistically or on average, but there are certainly places that are more neutral than we thought at even lower redshift. That's the result when you have all these sidelines to work with. So how about an even higher redshift? I said when you go to redshift 5, 6 also, the complete computing trough tells you that lamar give you no information anymore because they're black. Black is black, 0 is 0. You can never measure up to that of 10 to the 5 or something. There is when the Quasar and the region around Quasar comes in. And the best example is shown here. This is the first redshift 7.5 Quasar that was discovered by Eduardo Pinedos a few years back, 5 years ago. And that's a spectrum, sort of a matched spectrum. That's a spectrum itself, and the red line is a matched composite to try to predict what the Lam alpha line is supposed to look like. And that's zooming in over here. What you see is that, first of all, this is the redshift, this is redshift wavelength. That's the Lam alpha is supposed to be. The flux doesn't go to 0 immediately. Instead, it takes a few megaparsecs to get there. And that's because quasars themselves are are UV ionizing sources, so they're going to ionize the bubble around them. That's the size of the bubble. But also, you see the Lam alpha is much weaker than what you expect. And these are different realizations of trying to random model what they expect to be. And not only is weaker, it don't even have absorption on the red side of Lam emission line, sort of clearly off resonance absorption. And that's because if this part of IGM is really neutral, then your Lorentz line wing is going to begin to absorb things away. So you can model this damping wing, in fact, and use that together with the size of this near zone, this highly ionized zone around it, to estimate, to measure the neutral fraction of the intergalactic median beyond what you can do with an MR forest. And that's sort of damping with maintenance that we've been doing. And this first is actually the second object that people try to do that. Give you a damping wing, give you a neutral fraction of 50%. So basically they said, at least along this sightline, redshift 7.5, the universe may be half neutral already. And just to show you how that works. So basically this is an increasing neutral fraction. And then you will see that because of damping and absorption, that alpha just keep on dropping away when you go higher and higher neutral fraction. That's how you measure the neutral fraction with the damping wing plus near zone size modeling. So that was the first couple of measurements shows that, well, maybe a redshift 7.5, the universe was pretty neutral. Now we have more quasars again. We can do more. And then things become more sort of scattered around it. Scattered a lot, the thing word I use a lot here, gets scattered again. In this case, this redshift 7.5 quasar we actually introduced earlier. And this is the Lam alpha line profile and the blue one is the reconstructed, predicted, sort of PCA predicted blue side. There's not much absorption to speak of at that point. This actually has rather weak damping wing, which has some low neutral fraction at the same redshift. Last one, the redshift 7.5 is half. This one is much lower. Then we have another redshift 7 quasar, and this one has the strongest damping wing we know among those quasars. So neutral fraction could get higher. I think that just only 4 sidelines so far. We're able to do that. We'll be able to do more soon, I think. That tells you, even on the 4 sidelines, things are not uniform. Of course, the quasar, the great thing is you're doing individual objects, so you know exactly where things are happening. So to summarize the quasar reionization result, this is a paper that we're about to submit soon by undergraduate Xiaohui Jin at Arizona, where she actually summarized all these different results based on quasar measurements themselves, from the damping wing to the Gauss-Petersen absorption. And these blue light are newer, these points are newer points coming from so-called dark pixel fractions, which doesn't give you a measurement, but give just by looking at how much of the quasar spectrum is totally dark, give you a secure upper limit of the neutral fraction. And it tells you that quasar, the neutral fraction is high with large scatter at redshift 7.5. And we don't really know what's going on there yet without a lot of measurements. This is the trickiest part to measure things. And these are some of the models, whether it's from CMB or from some of the models of combined various galaxy measurement with CMB constraints. So I think the next stage is really to look at this stage where we have plenty of quasars. We don't have very good observations or measurement of these things yet, because these are the part just Lemma doesn't work. Damping wing doesn't quite work either. We're trying to figure out whether we can improve this part, but this is also the part that there's like 2-3 order magnitude increase in neutral fraction by redshift 6 to redshift 7. So I think that is actually the frontier of the quasar using quasar polarization is actually in the middle. All right, so I'm gonna spend the last few minutes talk about what happened next. I already said that we may be able to get to redshift 9 or 10 and we're done with quasars. But that requires things like Euclid and Roman to work and LSFT or Rubin to work. Before we do that, before the next generation of surveys can allow you to even push quasar to even higher redshift beyond redshift 8 or so, I think the next few years answer is really JWST. We're really excited because the quasar community through GTO and GEO effort put a lot of proposals in and put a lot of and thank TAC for approving them. And there are a lot of data that's going to be collected of the quasar that we have discovered. And this just summarized the maximum magnitude versus redshift. And all these red points will have some JWST observations in the next year or so, just in cycle 1. That includes these 3 sort of post-shelf highest redshift quasar frontier, which actually we are going to use almost all the mode possible in all the instruments to just get to figure out what's going on in these 3 objects, because we're not going to find many more of them. And then when you go to lower redshift, we have a large sample of objects that we're going to, in addition to quasar themselves, map their environment to ask questions sort of the quasar galaxy, large structure connection. And then you can see that it also spans over a very wide luminosity range, not only to probe the luminous ones, but some fainter ones as well. So we're really looking forward to this JWST programs that really will get a long way to some of the questions that we're trying to answer, including we are going to improve the black hole mass by looking at better spectra at longer wavelengths with better SEDs, and also constrain the ATN structure by looking at longer wavelengths SEDs that we don't know before. But probably the most exciting one is actually we're going to see the host galaxy. So the HS, you cannot do it, but now this is the PSF, quasar with the PSF quasar, and then the host galaxy behind it. And if you can do reasonable PSF star observations, we think we can actually see the host galaxy fairly clearly, even though when the host galaxy is only a sort of a couple % or something of the quasar themselves. And this is the simulated IFU observations of the quasar host galaxy, where you're going to see multiple lines with velocity fields and maybe some indication of outflow and listen, all the kind of good stuff. And then we have the redshift survey in the quasar environment using slitted spectroscopy on JWST to actually measure individual galaxies, both in the Quasar environment and along the line of sight to do things like IGM galaxy connections and then improve the constraint on reionization history. So that's something that I think will be really exciting, and we'll hopefully in the next year or two we'll actually have some interesting answer to some of the questions we asked earlier. All right, so I'm going to wrap it up, and I think there are three things I want you to take away. Three figures I want to remember. One is this one. This is the black hole mass versus time that make the point of sort of maybe early these massive redshift 7 quasars have to have very massive seeds. So I want to argue that, well, I think in the next decade, we're likely going to discover the first luminous quasars within our cosmic horizon. But much harder problem is to go there, is to go to fainter, earlier, more obscure place. And answer to that is probably beyond what the current or the planned facility can do, but really need X-ray stuff to go there. And of course, eventually, Lisa will tell us a lot. So that's the hard part. That's the question that a lot of us working on Quasars really motivation is, but we're not quite there yet. In terms of galaxies, this is the plot I want you to remember. They're just still a nice and diverse range of Quasar host galaxy through their star formations, through their gas kinematics. So early quasars are in very diverse galactic environment. And in that sense, interplay between galaxies and galaxy growth and black hole growth is still complex. We don't really have a M sigma relation to speak of. We only know some average trend there. And I think JWST and JWST ALMA synergy is going to make a lot of progress in the next few years. And finally, reionization, which is actually turns out to be one that I think we can really make a lot of progress fairly quickly, is because this hole here, redshift 6.5 to 7, is not that hard to observe, whether it's for quasar or through galaxies. And we can really map out this part of the parameter space fairly well. And luckily, there are plenty of galaxies and quasars that we can observe very well within this redshift range. Okay, so with that three spots, I'll stop here. Thank you.
Thank you for a great talk. And we have questions.
Well, I have a lot of questions, but I will just ask one and give one comment. So the comment is about the M sigma relation.
Yeah.
So basically, the very fact that you're observing Eddington limited quasars, which are really massive, tells you that they're exactly where you expect them to be, because the M sigma relation is bulge, basically merger-driven growth. And here there are no mergers, so they're growing by accretion, and so they become overgrown for their hosts. So this is absolutely what I would expect. And the question is about the seeds, because at redshift 0, we observe black holes, active black holes at masses around 15,000 solar masses, 70,000, so in the IMBH range. And this thing actually, you can squeeze the direct collapse hypothesis for the massive seeds to explain them, but you really need to keep them not growing for the Hubble time.
Right.
And then suddenly starting growing right now, because now we see them, and some of them are actually adding to limited accretion.
Right.
So basically, the question is, can there be multiple channels? So like you have both massive seeds and low mass seeds, and but the fact that you observe these quasars, you just pick up the ones that originate from massive seeds, but the ones originating from stellar mass.
I think totally that can be, right? Because there's nothing wrong with, I mean, this problem is only a problem if you are assisting, if you go to the highest redshift. You're looking at redshift 4 quasar, you don't have that problem anymore. So there's nothing wrong with growing something from 100 solar mass and just keep going when you have more time. This is really just it's really the test we're doing here. I think is really to ask question whether population stars can be the seed, or even stellar mass sort of not population stars, even lower mass can be the seed, but whether they are direct collapse black holes, whether you really need it or not to some of these objects. So there clearly can be multiple channels. Black holes don't know what when they're formed, they don't know what they are, right? So they can only agree. So yeah, I agree. We can be multiple channels. I don't know how to prove that in low redshift, and in high redshift we can push to see whether we can rule out some of them.
What kind of systematic error would you be comfortable with for both the black hole masses and luminosities? Is it possible that simply the scaling relation that you use to direct mass is giving you an order of magnitude?
Right. So that's why. So I mean, the few answer to that, right? So first is, I mean, so serial relation actually is really tricky because I mean they're not tested on the high luminosity end at all. We don't have these quasars we're talking about in local universe to do this. We don't have them to do radiation mapping because grad student career is too short. They're very so they're 10 to 10 solar masses. They're not going to vary the time scale. They're relevant for us. So that's true. But even just you assuming Eddington limit, you still give the same order of magnitude, same number in factor of field. So that may be okay. And of course, quasars don't really change very much, give you some confidence in scaling. And then of course, the real answer, I guess, is reading the matter of the black hole mass themselves rather than using scaling relation. That will be great. I mean, but of course, you get an argument of whether you believe gas dynamics to matter black hole mass at all, even in local universe, that's another problem. But that's better than reversion mapping, at least I think one step at a time. We are not do stellar dynamics of these objects anytime.
Yeah, there should be some redshift above which there aren't any metals, right? You just got primordial gas.
Yeah.
Accreting. Now you have not found any object in which you just see hydrogen lines and no carbon.
Not in quasars. Not in quasars. In galaxies, there are arguments about it, but certainly not in quasars.
Does that begin to set some interesting limit on the rate of star formation in metal?
Sure. Yeah. I mean, because all the quasars we observe are dusty, but they're still a few 100 million years. So I think that is and for quasars themselves, borderline regions, are not that big. It doesn't take very much to enrich them. I think it's really actually the dust part is interesting because they all have high dust mass.
Yeah, there's not much time to produce
Yeah.
dust.
Yeah.
Christina?
That's a very nice plot from Genie Young's paper with the composite spectra from like redshift 2, not exactly the same, or 2, yeah, that one exactly. It's maybe not too surprising, right? Because the way you find these high redshift quasars is you take the low redshift quasar and then move it to the color space where you would expect it to fall in redshift 6. Do you think this could be a selection effective, or would you have found any quasars that would look very different?
I mean, the color selection is not very strict. These are just drop out, and we take everything that. I mean, so one thing that they will affect things is redden quasars. The ability to do redden quasars getting worse. So we're just looking at things and not obscurity. If you take the reddening part out, then argue we're not going to mean we do see weak-line quasars at high redshift, maybe even more common. That's one thing we didn't talk about, but could be. But otherwise, on average, since we're not missing weak-line quasars, which are harder to find, I think we're okay. The dust part, we don't know. I mean, we have very few examples of very dusty quasars because we can find them. If they're dusty, they're redder, and it's very hard to tell them apart from dwarfs.
Does dust play a bigger role as you approach the redshift 6 and 7 regime?
The dust
There'll be more dust there than it would be earlier on. And all the scatter that you were showing, I wonder to what extent would that be dust related, and that relates to star formation rate?
So, I mean, we really don't know how the dust get there and whether this dust is different from local one or not. I mean, I would assume dust is easier problem than higher redshift, but doesn't seem to be the case. I mean, the one object that we just talked briefly, this super massive thing, that one actually has weird dust properties. We don't even understand what's going on. They could be different, and there are other examples like that. There could be different dust properties in these objects. I don't think maybe JLST has a long enough wavelength to tell us that. We don't know.
Ron, do we have any question on Zoom? Okay, so any more question for Xiaohui? If not, we should thank him again.